This video is going to introduce us to mathematical proofwriting, specifically what it is and the tie-in between proofwriting with mathematics and logic that we've been doing previously with the predicate calculus and the truth tables. So first of all, what is mathematical proofwriting? At its very base case, mathematical proofwriting is simply a very formal way of explaining why something in mathematics is true. That's it. You're essentially proving why something is true or explaining why something is true. Now, there is way more specificity to that than what I just said, so let's get into some of the details. Okay. First of all is logical format of mathematical theorems. And remember what a theorem was. It's simply a mathematical fact, so it's something important to remember. So the format of these mathematical theorems goes as follows. Now this is grabbing our symbolic logic again. You've got some condition P1, some simple statement, some condition P2, so it's P1 and P2 and P3 and all of these other preliminary guys that you have to have ahead of time. Then you've now got an implication, and according to the mathematical theorem, if you have all of this starting point to begin with, however many things you have in your starting point, you will get to some conclusion, so that Q right there. Now, how would we go about explaining a mathematical theorem and why it's true? In other words, how would we go about proving some mathematical fact, proving some theorem? Well, it turns out what you have to do is you have to show that this implication that we wrote out in symbols right up here, right above, is in fact what? It is in fact always true. Okay? So, how can you do that? Well, you can of course write a truth table just like what we've done in the past, but that gets a little bit unwieldy. Okay? Now, what are we going to be doing in specifics? Specifics, we're going to go from the assumption that everything in the if part of the statement, so all of these conditions, are going to be true. And then we're going to have to figure out, all right, does this force then that conclusion Q to always have to be true as well? And just as a side note here, remember the funkiness with the implication truth table. If you started off in a false location for your if part of your implication statement right here, then the part on the then statement is, it doesn't matter if it's true or false, the entire implication is still always true. What that means for us is if we're trying to show that the above implication is always true, the only case that we are worried about is what happens if your if part of your statement is true and then your then part of your statement is false. So we're eliminating that one line on our truth table for implication. Notice what that means. This means that we are in fact looking for a tautology, because a tautology is saying what? It says in all situations, regardless of what's going on here with our if part and our then part, we need to always, after we've assembled everything, to always have a true statement. Okay? So let's look at a couple of examples, and this is where we're going to bump ourselves out of purely symbolic logic and start looking at some sentences again. Okay? Now, fair warning, this is not mathematics right here. This is simply now looking at that same logical structure of putting things together. So for this example, we've got three sentences. The first sentence says, if I drive to work, I'll be tired. The second sentence, if I'm tired, I'll miss lunch. And the last one is the conclusion, if I drive to work, I'll miss lunch. Okay? So let's convert this into symbols. Okay? So if you have something that's symbolic, whether it's words like what we have here or whether it's math related, if you want to convert it into symbolic logic, you got to pick letters. Okay? So in this particular case, I'm going to go ahead and pick the following. I'm going to pick W to be the simple statement of I drive to work. T for I'm tired. L, I have lunch. And then if we convert these sentences into symbolic logic, the very first one would turn into if I drive to work, I'll be tired. So if W, then T. The second one will be if I'm tired, then I'll miss lunch. We'll notice miss lunch isn't have lunch, so this one here would be if T then implies the negation of L. And then our conclusion, or what we hope to be, our conclusion says if we drive to work, then I'll miss lunch. And we'll put that one together here at the end. Okay. Now, what does this mean in terms of checking to see if the logical structure is correct across those three statements? In other words, making sure that our logical reasoning is correct behind the scenes here, even more than just stripping out and rewriting those three sentences in symbolic terms. What this actually means goes as follows. It says that if I drive to work, I'll be tired. And if I'm tired, then I'll miss lunch. And both of those guys together, notice the and, implies the conclusion of if I drive to work, then I'll miss lunch. Okay? So this here's the idea behind whether you verify some logical structure when you're looking at proofwriting. Okay? Now, when we look at this in terms of proofwriting, will we always put it into a truth table? We could. So let's look at this particular compound logical statement right here and see what would happen if we put it into a truth table. Well, the first thing that'll happen when you want to put this into a truth table is you have to figure out how many rows they're going to be. Okay. Now, in our case, we have several simple statements. So I'll write this to the side in Scratchwork. We have the simple statement W, we have the simple statement T, and we have the simple statement L. So since there's 3 simple statements, this is going to give us 2 to the third, or 8 rows is how many rows we need to have here. Okay. Next thing is we'll actually go ahead and draw out our table. So we've got W, T, and L, and it really doesn't matter what order you put those guys in. You just have to put them all at the beginning. Next, we'll go ahead and do all of the possible combinations of true and false. So here, if the first 2 guys are both true, L could be either true or false. Then you've got to get some other combinations for the first 2 slots. So if W is still true, T for tired could be either true or false. Well, we already have true, so it should be false next. Okay. And then this allows you to have L to be either true or false. And then we can do all 4 of those same combinations except when W is false. So I'm just going to copy these guys down again. So we have false, true, true, false, true, false, 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 true, and false, false, false. And this now tells us how long our table is going to be as well. Then we go ahead and we build out all of our intermediate columns. So I'm just going to read here by order of operations. We've got W implies T is somebody we're going to need to worry about. We're also going to have T implies not L. Well, in reality, we need to worry about not L first. So let's go ahead and put in not L. Honestly, I'd normally put not L earlier, but if you didn't notice it until right here, it's totally fine to put not L in this column as well. Then we still need that implication of T implies not L. We'll need to go ahead and do the and of these 2 guys together. So W implies T, and T implies not L. And at that point, we've done everything we can on the if part of the really big if-then statement. So next we need to worry about these guys on the other side. Now we already have not L, so we just need to figure out W implies not L. And then the only thing left is the actual full statement. And since this statement is too big for me to write in the space that I currently have right here, I might be able to make it really tiny. So W implies T, and T implies not L. Whole thing implies W implies not L. So it just barely fits there. Now we just need to fill in all of these rows. Okay, so let's start at the beginning. So we are looking at W and T, so the first 2 columns that we have here. We know that if you start with a false for an implication, it doesn't matter what the then part is, the truth value of the entire thing is going to be true. The only time an if-then statement is going to value out as false is if you start with a true and end with a false. So these 3rd and 4th rows are going to be false, and everybody else will be true. Then we look at the column not L. Not L is going to take all of the guys in L and just flip them. So first row we're going to have, well, it was a true, so it's now going to be false. The false, now a true. And then we'll keep going and doing that same exact thing. Next we have true, not true. This was tired. Tired implies not getting lunch. So here we're going to look at the column of tired, the column of not lunch. And remember, the only time that this implication is going to be false is if you end with a false but start at a true. So first row we started at a true and ended at a false, so that'll give us a false value. The next one, we ended a true and started a false, so that'll be a true. The next one is true, then false, so that's a false. False, then true. True, then false. False, then true. True, then false. And false, then true. Next thing we've got, next column over, is we're going to look at ands. So we're looking at the column here of the W implies T and T implies not L. We'll and those together, and remember with an and, the only time you're going to get a truth value if both of them value out with true. So here, first row is going to be true and false, so that gives you a false value. Second row is true and true, that's the only time you're going to get a true value. And we'll fill in the rest of these doing the exact same idea. Next, we go on to the next column, and we'll look at W implies not L. Well, we've got W and we've got not L, so they're right here, first column and what is that, the fifth column. And in this case here, we're again looking for W, we're looking for when you have a false and in the then statement and a true in the if statement, and that's the only time we're going to get a value of false in our truth value here. So that first line will still be false. Now, as we move down to the next row, notice it's true implies true, so that's just fine. Next one is true implies false, that's a problem. The next one is true implies true, so that's still cool. And the last ones are all going to start with a false, so it doesn't even matter what goes on the other side. We're going to get trues for the rest of this. Okay. And then we're ready to finish ourselves up. So last column right here is going to be our ands, so this one here. And then, so that's the if part. The then part is the bit we just figured out. Okay. So in terms of what we're doing here, notice what happens here. It's an implication overarchingly. So what we're going to be looking for is the only time that this would value out as false is if you have an if true then false. Well, notice where the thens are. Thens are here, and the only time the thens are false is on the first and the third row. So we check backwards to our first and our third row where our if statement comes from, and the only time we're getting a false in our conclusion is if we started with a false. That, in terms of your implication, is a truth value of true, and everybody else is either true implies true or false implies something, all of which are going to give you a truth value of true. So we fill that all in, and notice that in our final column, that right there, we get a truth value of all true for all of these guys, which then allows you to say, all right, well, I can figure out the truth value of this original statement. It doesn't matter what's going on with our three simple statements of W, T, and L. We know that the overarching truth value is true. Now, take a second, remember what that means. So, bumping back to the logical structure, okay? Not looking at the underlying truth table anymore. What we need in order to say that our logical argument is correct, is valid, with everything that we've done so far here in this small example that deals with lunch. What we would need to say that our logical argument here is correct is if you get a tautology in the underlying truth table. Now, we got that this compound statement right here did come out to a value of true the entire time, which meant it is a tautology, which means this argument right here is a valid argument. And actually, it's a very, very classic way that we link facts together to get a conclusion. In fact, it's such a common way of linking facts together to get a conclusion, we actually call these ways of linking facts together to get some nice conclusion. So they're called rules of inference. And there's lots and lots of different rules of inference. However, we're going to focus in on just two of them. Okay. So the first one here is exactly what we just did, which says if P then Q, if Q then R, and then the natural conclusion that we should jump to is down here at we should be getting if P then R. In other words, you're literally able to link all of these guys together. Okay, so that is probably one of the guys that we use tons and tons and tons. Now, the next rule of inference that we have says you know the implication if P then Q is true. You then are told you have something inside of that situation of P. whatever that P statement is, then what should you conclude? Well, naturally then we should conclude that we are getting that conclusion of Q from our implication. This last one here is actually called a special name called modus potens. And let's go ahead and grab one last thing that we've actually talked about already. And this setup is almost identical to modus potens. No, it's not, but it's similar. This one here says, again, you have an implication. It says anytime, you know for sure that anytime you have P, automatically you have Q. You've been able to verify that you don't have Q in any way, shape, or form. Then the assumption is, what can you show? You can say that, hey, we're not going to be able to have started at a starting point inside of P. This is called modus tollens. Specifically in non-Greek terminology, this one and 2 are both considered a direct proving method. And 3 over here is using a contrapositive, if you remember the buzzwords for the different type of related implications. Or statements that were related to an original implication. So let's look at an example, and this is not an example with actual things for your statements, it's just going to be symbol pushing. So suppose you have the following. Suppose you've got the same setup as those last 2 rules, actually all 3 of the rules of inference. You know for sure that if you have P, then you have Q. Okay? So this is the question. Suppose you then have, and you know for sure that you do not have P. Okay, you've been able to establish this. So the question is, could you then conclude that you're guaranteed to not have Q as well? So take a second, make a guess, see what you think. All right, and it turns out that this is actually an invalid argument. And the first time you've ever seen this, you might be very much doubting it. If you've ever seen it before, be like, oh yeah, I know that. But if you've never seen this before, say, whoa, what just happened? So here's the idea. I'm going to tie this back into sets. Okay? So if you have if P then Q, so that's something we said we established. This can be represented as a Venn diagram. Okay? Specifically in the following way. You have some big set that we'll call Q, some smaller set that we call P. So notice what happens here. If you are inside of set P, you are guaranteed to also be inside of set Q, because notice here P is a subset of Q. Okay? So that's how to turn this logical implication into sets. Now remember what we know about sets. There's options. So if we then look over at our example, if you look at somebody who's not in P could be out here. And if that's where you live, not in P, you're also not in Q. And that would imply that this argument is valid. But take a second, look at that picture. Could you actually come to another conclusion? And the answer is yes. You could also pick your little point that's not in P, but is also in Q. So in terms of the conclusion, the logical deduction over here to the end, if you are not in P, there's no guarantee that you're also not in Q. You actually have options here. You could be in Q, but you could also be in not Q, and we just don't have enough information to be able to tell. Okay? Notice how this distinguishes itself from the modus tollens, in other words, using the contrapositive. In this case, you start off with the same if P then Q, so you've got the same idea of little p set inside of big Q set. Here, if you start off by being not in Q, notice you are guaranteed that there's no way you're going to be inside of P. You're only going to be forced to be in not Q. Okay? So that's the distinction between these two guys.